All right, so this is better. Okay, let's see. Is it recording? Yes. Yes. Okay, so we are recording. All right, so this is lecture 9 and 21st of April. So where were we last time? We started with, you know, categorizing the vibratory motion. I told you that the course is divided to these two classes of vibration, free and forced. And in each case, we have undamped and damped systems. Okay. Of course, we have already studied the free vibration of undamped system. So we started the second category of the four possibilities, which is the free vibration of damped systems. Okay. And so basically we have a system like this that consists of a component, the damping component, or the system is damped and is experiencing free vibration. And the equation of motion, as we derived it, looked like this, right? And we solved this differential equation, which is linear, homogeneous, ordinary differential equation by setting up the characteristic function. Okay, oops. This, which led to these two roots. I set up the two roots, 1 over 2m minus c plus minus c squared minus 4km. Okay, and so we substitute these two roots in the general solution, and we end up with a solution which takes this form. Okay. And as we said last time, so this is the sort of the solution in terms of these two roots, right? And as we briefly discussed last time, we noticed that although we have two distinct roots for this characteristic function, but the two roots depends on the value of what we have under this radical. That is, if this C2, C squared is equal to 4km, this will become 0, so the two roots would be equal. We call this value of C 2km, which we in fact demonstrated it can be written as 2m omega n. We gave a name to this. We call this critical damping. So the critical damping coefficient. Okay. So in this case, if this happens, as we discussed briefly last time, that means the two roots would be equal. Solution of this equation, or the response of the system, or the motion, will take this form, e to the minus omega n t. Okay? And that's where we stopped last time. So this case that the two roots are equal, we want to elaborate on that a little bit more. So what I'm going to do is this. This was the equation of motion, right? I would rewrite this differently. You remember if we had the undamped case, of course, in that case, it was not that significant to rewrite the equation in the alternative form. But nevertheless, as I said, if you divide both sides by m, this equation became something like this. K over mu is equal to 0. K over m is omega n squared. So this was an alternative form of writing the equation of motion. We'll do the same here. Let's divide both sides by m. So you have u double dot. So keep this in mind. This is one form of the equation of motion. Now I'm going to divide this both sides by m. So you end up with something like this. K over m, u is equal to 0. This is the natural frequency squared. But how about this? May not seem to have that significance, but let me rewrite it in a different form. Instead of c over m, I would multiply that by this critical damping ratio, a critical damping value, okay? And divide it by that. In other words, I'm just multiplying this by 1, right? But I will rearrange this and write this at c over c sub c times c sub c over 2m, right? Remember, c sub c from here is 2m omega n. So this part becomes what? Just 2 omega n. This ratio, which is the ratio of the damping coefficient in the system and the critical damping, we assign a name to it. We call this damping ratio. And we use a character to show this, character zeta. So the equation of motion then takes this form, u double dot plus 2 zeta omega n u dot plus omega n squared u is equal to 0. This is the preferred form of the equation of motion in the case of damped systems, and I will show you why. First of all, in this form, you have one of the two important dynamic characteristics of the system, which is natural frequency. Damping ratio, which we introduced, is also another dynamic characteristic of a vibratory system. It is almost, for the lack of a better comparison, it is like the coefficient of friction that is unique to any material, right? Damping ratio is unique to any system, like structures, for instance, a structural system like a steel building or reinforced concrete building. This damping ratio is almost something like 1 or 2%. For mechanical system, depending, of course, on the type of mechanical system, is anywhere from 3 to 5%. Okay, so it has a significance, and that's why we prefer this form. Okay, so let's move on. Let's see, with this formulation, what else we are going to do.
Quick question before we move on.
Oh, sure, please.
On that previous page, after the damping ratio, the first time that you write that, where it's cc over 2m.
Right, this one.
What does that say right after the m?
Oh, this one? Well, I substituted for c sub c, which is 2m omega n, right?
No, sorry. On the denominator, there's like a Is
Oh,
that
this
just a dot or?
just divided by 2m. Oh, I just noticed that C sub c is 2m omega n, so I had just dropped that. So denominator is 2m omega n.
All right, thank you.
Sure. Oh, no, wait a minute. Sorry about that. What did I do here? No, I separated these two. So C sub c, C or C sub c, and then I wrote it that way, right? So in other words, I separated these two, and then C sub c over m. So this should be just m. So C sub c is 2m omega n. Denominator is just m, not 2m. Okay. So this whole thing then becomes 2 omega n, because m and m cancel out. So this becomes just 2 omega n. Thanks for noticing my error. Does it clarify?
Yes, thank you.
Okay, great. Thank you. All right. So that's where this 2 comes from. So now that we have this form, let's look at again the roots of this equation. So the roots of this equation in terms of this form, if you redo that, reset up the characteristic function, will this form, okay? Plus and minus 1/2 times 4 zeta squared omega n squared minus 4 omega n squared. Okay, so this becomes the shape of the two roots, or if you simplify that, you get, omega n comes out of the radical, so I factored that out. Okay, then I have z, okay, that will become negative zeta plus 1/2. What I also do, once I take this omega n out and 4 becomes 2, so that cancels out, I end up under the radical, I end up with zeta, okay, minus zeta squared minus 1. What I do, instead of zeta squared minus 1, I will write it like this: negative 1 times 1 minus zeta squared. This negative 1 is I, so this becomes I times 1 minus zeta squared. So this becomes the shape that these roots will take now in this form of the equation of motion. So these are the two roots now. Now look at these two roots. We said that if under this radical, or if this radical becomes 0, that is sort of the distinct case that separates the nature of the vibratory motion. Given that we have set up the roots in terms of omega n and zeta, now I will categorize the different values that these roots will take. If you look at zeta being greater than 1 here, what happens? If zeta is greater than 1, right, this would become a negative value. That means you have a negative square root of 1. With this multiplied becomes 1. So the two roots in this case, okay, are going to be real numbers and distinct. In other words, you have two roots that are not equal, they're distinct. Okay? And what happens if zeta is equal to 1? If zeta is equal to 1, obviously this is 0. So you have roots that are equal, okay, and obviously real values. So the equation, I mean, the characteristic functions has two equal roots, okay, and they're, basically the same. Their third possibility is if this zeta is less than 1. If zeta is less than 1, right? So you have this I here, right? So the roots become complex numbers, but they are distinct because you have plus and minus here. We assign a name to each of these cases. When zeta is greater than 1, what does that mean? That the damping ratio coefficient in the system is larger than the critical value of the damping. So we call this system an overdamped system. If zeta is equal to 1, that means the damping coefficient is equal to the critical damping. We call this critically damped system. So that's for this case. If zeta is less than 1, that means the damping ratio in the system is less than the critical damping, and we call this an underdamped system. Okay? So now with these definitions, I'm going to look at now the solution of this differential equation, or u of t, which, as you can see, it depends on these different three cases of damping ratio. So I will begin with the case that the damping ratio is greater than 1 or an overdamped system. If you have an overdamped system, these are the two roots, right? These are the two roots. So the solution would be what? A times lambda 1t. This is lambda 1, which is negative zeta plus the square root of
I see what you're seeing.
zeta minus 1 omega n t. Since zeta is greater than 1, I write it like this, okay, omega n t. And then you have b times e to the minus zeta minus zeta squared minus 1 omega n t. So this would be the solution to that differential equation. Okay, so of course I did a little bit of mathematical sort of manipulation here because you have zeta greater than 1, so I took the negative sign out, so it becomes this. So these are the two, this is the response. But let's look at here, okay? You can simplify this. You can write it at a e to the minus, if you look at this, this is minus zeta omega nt. This has minus zeta omega nt, right? So you have e to the minus, okay, let's say if I call this whole thing alpha, okay, minus alpha t, okay, plus b to the e minus beta t times the square root of minus zeta squared minus 1. Okay, so in other words, if you look at this, I have this minus zeta omega nt, right, which I would factor that out, times this for each case, right? So if you simplify that, you have basically something like this, okay? Maybe I would not skip that operation. So let me and that mathematical form. You have a times e to the minus zeta omega nt times e to the minus zeta squared minus 1 omega nt, right? That's this one. Then you have b times e to the minus zeta omega nt, right? Times e zeta squared minus omega nt, right? So I can factor this out. So you have a plus b times e to the minus zeta omega nt plus, okay, these two. You have a, okay, um, uh, a times minus c squared minus 1 omega nt plus b minus, this would be actually plus z squared minus 1 omega n t, okay? So you can simplify this whole thing. You can write that basically if you c to the e something times t plus d minus beta t. So you have the sum of two exponentially decaying function, okay? If you look at this, okay, this is an exponentially decaying function. This is an exponentially decaying function. So instead of, in fact, even going through these, I could have shown you directly that this value, because zeta is greater than 1, is larger than this value, right? You can see that this is zeta plus some value, which is greater than 1. This is zeta minus that. So this value is greater than that. So you have two functions that are exponentially decaying. This is obviously larger than beta, but doesn't matter. What you have two functions. One of them is like this, okay, with a steeper rate of decay, exponentially decaying function. One like this. Sum of these two results in an exponentially decaying function. So the conclusion is, if you have a system which is overdamped, okay, is an overdamped system, the response will be an exponentially decaying function, which, depending on the initial values or the initial conditions, can have one of these forms, like this, or goes like this. In this case, of course, this is u of t. The initial velocity, which is the slope of the curve, is positive. In this case, initial velocity is 0. And in this case, the initial velocity is negative, okay? Or it can be of this form, depending again on the initial conditions, okay? Can be like this form. But regardless of what the initial conditions are, for the case of critically damped system, okay, you see that the vibratory motion is exponentially decaying, and it would not reach equilibrium. In other words, u goes to 0 only when time goes to infinity. theoretically speaking, of course. So you say, okay, you wonder what kind of a system it is that once, you vibrate it or make it to vibrate, it will never go to back to equilibrium. Of course, again, uh, theoretically speaking. These are systems that, very, very rare, and they're mainly mechanical system. Means a structural system, you never have an open dam system. An example that I always give when I'm teaching in physical environment is these door stoppers. You open the door, you have this hydraulic device at the top connected to the door. When you open it, okay, you want the door automatically closes. So that's what this does. But the damping is so high that you feel like almost takes forever for the door to close. That's one example in real world. Another example is the case that of a system that goes back to my early childhood. Those turntables. You have a turntable gramophone. Okay, you have an arm that you lift it, and then you let it go down to sit down on this LP to play the music. There's a needle here, and you want, when you move this and let it go, the motion would to be exponentially decaying. So theoretically speaking, it would take this forever to smoothly land on this LP, or basically this comes to an equilibrium. Okay, so that's how they designed the damping system for these arms of the LP system. Okay, but anyway, this zeta greater than one is very, very, very rare to encounter in any mechanical system. So let's move on. The second case.
Could I see the page before, just the end of it, please?
Or the page before, you mean here, or
With the alphas.
or these? Let me actually redo this, because forget about these, because I realize that in fact would have been easier if I can just show it here. You have e to the minus zeta times this omega nt, e to the minus zeta this, right? The only difference between these two exponents are this is plus, this is minus. So I call this to be alpha, and this component to be beta. So what is the difference between alpha and beta? This is zeta plus that value, this is zeta minus that value. So you can see that alpha is larger than beta, right? You can see that. If this value is something, and this is something, you're adding this to zeta here, you're subtracting it from zeta here. So alpha is greater than beta. So this is an exponentially function that has a steeper rate of decay or steeper slope than this one does. So this is that, and this is this. That's what I was trying to say. But who cares? All I want is the sum of these two exponentially decaying function, which would be an exponentially decaying function. That's what I was basically saying. So, which means function would have one of these forms, exponentially decaying. Does that answer your question?
Yeah, thank you.
Great, thank you. So we move on, because this is not much of an interest. We move on to the case that damping ratio is equal to 1, or we call that critically damped system. So let's see what happens here. In this case, the two roots are equal, and the two roots would be negative omega n. because if I go back here, if this is equal to 1, right? So this becomes 0. So the two roots would become what? Would be just simply, I'm sorry, negative omega n times zeta. Okay? So if you substitute for that, you will see that this response will take this form. I don't go through the derivation of that, but remember, we recall from differential equations, solution to differential equations, that's what the two roots would become. Okay? So now look at this function. It consists of two parts. This exponentially decaying component, and then this linear component. What does that mean? That means you have an exponentially decaying function multiplied by a linear function. So this can go to 0 at some value of t, which is negative a1 over a2, right? This cannot go to 0 except when t goes to infinity. So what is the shape of the response in this case? In this case, the response has the possibility of going to 0 only once, but stays nevertheless as an exponential function. So it can be something like this, or something like this, or something like this, depending on these initial values, okay? So that's the shape that this critically damped systems, again, of course, you can have also depending on the initial displacement, because this is the initial displacement, right? If the initial displacement is negative, you can have something like this. But anyway, that's what the response would look like. It can go to 0, but it will go back quickly to becoming an exponent, continuing that exponential function that reaches 0 when t is equal to infinity, okay? So you wonder what kind of a system that is. That is a critically damped system that goes to 0, that means comes to equilibrium, but the exponential decay continues. This is the case of suspension systems for sports cars. In more luxurious cars, expensive luxurious cars like sedans, you don't want that. You want, if you go over a bump, vibration or vibratory motion decays out and goes to 0 fast. But in a sports car, you want to have that joy of feeling the bump, but yet, of course, vibration dampening out. So that's the way the suspension systems in those cars work. Again, this case of critically damped system is not that common. The third case, which is the case of damping ratio is less than 1, is the case that we encounter in mechanical or structural dynamics. And that is the case of underdamped systems. Vast majority of the systems that you encounter in real world are underdamped. Okay, we don't, especially in nature, we don't have overdamped or critically damped. Maybe occasionally we have, but I would say with confidence that 90%, more than 90% of the system we encounter are underdamped. So what happens in this case? The two roots were this, right? Minus zeta plus and minus I 1 minus zeta squared omega n. Okay. So let me write the response then. Response would be A to e to the minus zeta 1t plus b e to the minus lambda 2t. So substitute for lambda 1, which is minus zeta plus this, right, omega n, and lambda 2 is minus zeta minus this times omega n. So substitute for lambda, you get something like this. You will get, okay, EA times e to the, see, in both of them you have this component, right? So you have e to the minus zeta omega n t times e to the positive omega n t plus b times e to the minus zeta omega n t, okay? And of course, in this case, you have e to the minus zeta, square root of that omega n t. So you can factor this out, okay? So what you will get, you get e to the minus zeta omega nt times a to the e, okay? Of course, I here, which I dropped. So you have e to the I times this omega nt plus b minus I, this is 1 minus zeta omega n squared t, okay? So e to this power, okay? So the response will then further simplify that. Response would become of this form, e to the minus zeta omega nt, okay? A e I times 1 minus zeta squared omega n t plus, I'm rewriting it more clearly, the minus zeta 1 minus omega n squared omega n t. So this is the shape that this response of the system when the system is underdamped will take. I'm sure you're going to say, I don't like this. Is there another way we can write this equation?
Professor, I have a quick question. For on the b term, should there be an I in the exponential term?
Yes, I'm writing this so quickly. Thanks for being so observant. Yes, correct. Because that's where that comes from right here. Yes. So for both of them, you have this. Okay. Okay. So let's take a look at this 4. That looks familiar if we pay a little bit of attention, right? What I have here, I have something like this. U of t is e to the minus zeta omega nt times a e to the I. Why don't I call this whole thing just something? Okay, in other words, I have e to the I size times like theta plus b times negative I e to the I theta. But if you look at this, now Mr. Euler is going to come to our rescue. What is e to the plus and minus I theta. It is cosine theta plus and minus I sine theta. So I will substitute that, of course, where theta is what? 1 minus zeta squared omega n t, right? So I will substitute for that form. So u of t then now takes this form. Will become e to the minus zeta omega nt times a cosine of 1 minus omega zeta squared omega n t plus I sine of 1 minus zeta squared omega n t plus b cosine of 1 minus zeta squared omega n t minus I sine of 1 minus zeta squared omega n t. Okay? But let's further simplify these because these two terms are the same. These two terms are the same. So if you add these up, you get e to the minus zeta omega n t, okay, times a plus b cosine of 1 minus zeta squared omega n t, okay, minus, okay, or you can say plus I times a plus b times sine of this omega n t. Okay, so let me further simplify this. If I further simplify that, you can see that you can write e minus zeta omega n t. And let me call this the square root 1 minus omega zeta squared omega n. Let me call this omega sub d. So you have e to the minus zeta omega n t times, this is a constant, so I write it at c times cosine of omega dt, okay, plus d sine of omega dt. So what I did was I considered this to be just a constant value, which is, and this another constant. So you basically have now this simple form, right? But let's pause a little bit. Look at here. We had this form before, right? I said that if you have something like alpha times cosine plus beta times sine, you can multiply this by the square root of alpha squared plus beta squared divided by alpha squared plus beta squared, right? And this value are the sine and cosine of a function, okay? Because the square of these added together is 1. So although this form is a nice form for writing the response of an underdamped system, I can write this part in an alternative form. So u then becomes basically this constant, let's call that e, times e to the minus zeta omega nt times the sine of omega dt plus something like this. In other words, this is, let's say, cosine of an angle theta. This is a sine of an angle theta. So sum of the two would be the sine of, theta plus alpha, okay? Trig identity, okay? So this is the alternative form that this response in this case will take. And this is the more preferable form. Why? Because you see that an underdamped system consists of a sinusoidal function with an amplitude which is decaying exponentially. In other words, if you plot this function, it looks like this. It has an amplitude that exponentially is decaying, but the function is in fact sinusoidal. In other words, goes like this. So this is the shape of an underdamped system response, motion of an underdamped system, which is the most common type of vibratory motion. This is obviously a period of this vibratory motion, which of course gives you the frequency. The frequency of this vibratory motion, which is 1 minus zeta squared omega n, commonly by mistake is called damped natural frequency. But the correct name for that is the frequency of a damped system. Frequency of this damped system is related to the natural frequency of a system, okay? We will see that this vibratory motion, that you will see that also in the lab, you're going to use that to, in fact, to find the damping ratio of the system is the most common type of vibratory motion. We will see that how we can actually by measure, plotting the response of an underdamped system, we can use that to find the damping ratio in a system. We will introduce that approach, which is the logarithmic decrement, next time. But also we'll study this motion because, as I said, is the most common type of vibratory motion. So I'm going to do a few problems next time and also introduce the approach of how you can use this vibratory motion to find the damping ratio of a system. So I'm going to stop right here. Okay, so let me pause the recording and I will stop here.